Hi everybody, I'm going to go over the projectile 2 motion, angled projectile motion, give you feedback on that since we're working remotely. Ask me any questions afterward because you're going to have a quiz on this. So we're launching something at an angle, we have initial speed, and we hit a target that's 80 meters away. So that's X, and we want to do a VTAX table on this. The first thing I ask you is draw a horizontal vertical component. So if this represents V0, which is 35, then some of that is horizontal, Vx, and the rest is vertical, Vy. We want to calculate those. So here's our angle. So Vx is going to equal V0 cosine of the angle, and Vy is going to equal V0 the sine of the angle. So you have the answers there, but I'll put them here. So that's 30.9 degrees, 30.9 meters per second, and 16.4 meters per second. If you're not getting these values, maybe you're in radian mode, so double check that. All right, now we can do the VTAX stuff. So let me set that up over here. So I've got X and Y, V0. So I know in the X direction, V0 is 30.9. I didn't help myself there by squeezing that in. So let me try that again. I really don't have much space here. Well, I'll just generate some space. X and Y. So this is 30.9. This is 16.4. Okay, there's V. Time I don't know about. Acceleration, that's 0 in the X direction, negative 9.8. And X, I know that the object is 80 meters away. I don't know what Y max is. I mean, there's 0 at the end of it, but I don't know. Okay, so how much time will it take the cat to be in the air? So I'm going to use the vertical part for time in the air because I know the initial speed vertically, I know the acceleration, and I also let me call that V0. I know the final speed at the peak is going to be 0, okay? So that's at the peak. So I'm going to say, all right, my time in the air is going to be equal to, I'm going to draw the generic equation, my final speed minus my initial speed divided by g, or an acceleration. And then I'm going to double that because if I'm using a final speed of 0, that's at the peak, so I need to double it for the total time in the air. What that translates to here is then t, and I'm not going to put in numbers because you can work that out, is 0 minus, and that's where we put in the 16.4. Do not put in the 35. Okay, we want the vertical component divided by negative 9.8, and then that's all multiplied by 2. And so we get an air time of 3.35 seconds. And then how much time to reach the peak? Well, that's just going to be half that, so that's 1.68 seconds. All right, next one. At the peak, what are the values of the following? Vx. Okay, how fast is it moving horizontally? Well, the key thing we remember is horizontal velocity is constant, so it's the same as what we originally found, that 30.9. What's going to be its vertical velocity? At the peak, we use that information to say 0. Horizontally, it's 0. Sorry, this is warped. It's a stupid smart board. And then this is always negative 9.8. So notice that it's always moving and it's always accelerating, but it's always moving in a horizontal direction and it's always accelerating in the vertical direction. Okay. Calculate the maximum height of the cat. Well, we have plenty of information for that on our VTAX because we now have a time to the peak. So maximum height means our Vy is 0 at the final, and our time was 1.68 seconds. So I can just say my delta y, because we start at 0, is V0 t. I'm going to call V0 0 because I'm going to pretend we're going from bottom to top. It's just a lot, top to bottom. It's just a lot easier to do it that way. You could put in the 16.4 for that and subtract off the 1/2 at squared, but I don't need to do that. So that's going to be V0 t 1/2 at squared. So that's 1/2 of 9.8. And again, make sure you use the 1.68. You square the whole thing, and you get the height. I don't have that off the top of my head. All right, where does a cat land relative to the target? So in other words, find the range. Range is simply x. So if I use this right here, the acceleration is 0, so that's just going to be Vx times t. We already calculated Vx earlier. So again, don't use the 35, use the 30.9. We want the full time in the air, so that's going to be our 3.35 seconds. And when we multiply those, we get 103 meters roughly. So that means if we subtract off the 80, that's where how far away it is, then we're about 23 meters beyond where we want to be. Okay, then we can ask what are the velocities just before it hits the ground. Vx hasn't changed. Remember, that's constant throughout, so that's going to be 30.9. Vy is going to be the same as our initial Vy, except in the opposite direction, so that's going to be negative 16.4. And then if I want to find the overall velocity, well, it's got to be 35, right? It's got to be the same as the velocity that we launch it. If you do Pythagorean theorem for these, you will get 35. Moving on. So what if we change something about the launch? So if the angle was changed to 62 degrees, we're launching at the same speed as before, what would the following do? So our initial angle was, let me remind myself because I've already forgotten, it was 28 degrees. Okay, so our initial angle was 28. So I note that 28 and 62 are complements. So if 28 is, if I sketch just a simple vector, here's my 28 and here's my 62, just so I can see that. I can see that the 28 is much more horizontal. So 62 is less horizontal, so the horizontal velocity is going to decrease. As less of that 35 is going to be horizontal, therefore more of it's going to be vertical. If it's more vertical, it's going to be in the air longer. The range has to do with how close to 45, so 62 and 28 are complements, so that's going to be the same. And the maximum height is going to increase because we're more vertical. Now let's compare to 20 to 28. So 20 is more horizontal than 28, so this is going to go up. It's going to be less vertical. Time in the air is going to be less. Range, all right, now 20 is further away from 45 degrees than 28, so the range is going to go down, and the maximum height is going to go down. Next problem. Now sketch the vectors that represent, for part A, the horizontal and vertical velocity. So at this height, we're going to draw some arbitrary vertical velocity and draw a horizontal velocity. At this height, it's all horizontal. This vector should be the same as that vector. And then down here, downward, this vector should be greater than this vector. And this one should be the same as the other three. So you want to be careful of that. Make sure those relative sizes match based on the height. Now draw a trajectory for 28 degrees. So this is 62, so 28 is going to go the same range, is not as high, so I might choose something like that. And then for 20 degrees, based on the previous problem, it's not going to go as far nor as high, so it might be something like that. So that's 28 and that's 20. Last problem. This is an important one, I think. Okay, we want to see if when you hit a volleyball, will it not only make it to the net, will it be at the right height to get over the net? So if she's 3.5 meters from the net, that's X. Will the ball make it to the net before hitting the ground? So basically what I can do is I can find the range and see if the range is greater than or equal to what we want to do, right? So in other words, is X greater than or equal to 3.5? That's how we answer that question. So to find a range, we need to find a time in the air. And I'm not going to go through the whole v-tex again. Okay, well, maybe I should. We know the initial velocity in the y direction. We know the acceleration. All right, so the initial velocity in the y direction is going to be 8.4 times the sine of 67 degrees. Okay, so we got to still do those component stuff. So maybe let me work it out here. Vy naught is v naught sine theta. The acceleration in the y direction is, of course, negative 9.8. And the final velocity in the y direction is 0. If we're trying to, I'm trying to find the time in the air. So, and then I'm going to double everything. So I'm going to use the same approach I did before. I'm going to say time is equal to twice Vy minus Vy naught. So since one of them is 0, it's just V naught sine theta divided by G. If I put in the numbers, I get 1.58 seconds. That's how long it takes before it hits the ground. Forget about the net. We don't know how the net's going to come to play. So X is going to be V cos theta. That's my horizontal velocity times the time in the air. There's no acceleration. So if I plug in 1.35 for this, do V cosine theta, I get 5.18 meters. So yes, it will make it to the net. Now the next question, will it be high enough to go over the net when it gets to that? So we need to know how high is the net. So what we want to find out is what's the height at X equals 3.5 meters. So there's a few approaches we could do here. I'm going to basically Oh, I'm sorry. Will ever go as high as a net. I'm sorry. So it can't make it over net if it never goes as high as a net. So I take that back. I just need to find the maximum height. Okay, so what's y max? And what I want us to understand about y max occurs when we're at half the time. So that's when t is half of 1.358 seconds. Okay, I can't read my writing there. So that's 0.79 seconds. So I can say, all right, I know the time it takes to get the peak. I know the initial velocity. I don't even need to know the time, right? I know the initial Vy, and I know the acceleration. So I'm going to say Vy naught is 0 because I'm just going to let it fall. That just makes it easier. So I can say the height maximum is 1/2 gt squared. You could use Vf squared equals V naught squared plus 2 delta y because you know the initial and final. That would work. You don't have to use the time. So the maximum height is 3.05 meters. That's taller than the net, so it could get that high. Now, ultimately, the tough question. This is where we'll finish up. Will it be higher than 2.5 when it gets to the net? So that's where I was saying, does y greater than or equal to the 2.3, that's the height of the net, when at 3.5 meters. That's where the distance is. That's our question mark. So let's figure out how high it is when it is at the that position. So what we can do is, this is one approach, we can find the time it takes to go 3.5. I'm going to put t 3.5. How much time does it take for the volleyball to move forward to even get to the net? Well, since that's forward motion, that's nothing more than x divided by vx. Okay? In other words, a distance traveled divided by the horizontal velocity, because there's no acceleration in the forward direction. So I calculate that, and you put in the numbers. The 3.5 is the x we want to travel, and the vx is the horizontal velocity, and that's going to take 1.06 seconds. Once I figure out it takes 1.06 seconds to get there, now I can solve for the height at 1.06 seconds. And in that case, I cannot say the final velocity at the peak is 0. I have to use v naught t minus 1/2 gt squared. And when I plug in the numbers, I'll let you plug that in, I get a height of 2.69 meters, which is taller than yet. So yes, it makes it over. All right, you can try number 3 based on the third tutorial where I did the bonus equations. I'll talk about those in class, but the answers are given. I believe B should be 6.12 seconds. I might put something else down.